Okay, hi guys. So this is the third review session. Last one before the exam, right? So I brought some apples as usual, so you guys can. I'm not sure if there's enough for all the sub problems, so we'll just give them out. I think the beginning problems are a little harder, you know. So I don't know, but you just take. I'll give them out at the beginning, and then there might not be enough. But that's fine. Okay, so who wants to do the first problem? So we have problem 1. Are the following compounds constitutional isomers, resonance structures, or neither? Yeah, actually, you know what? We can just maybe this one we can just do like each one. You know, who is for constitutional isomers? Okay, who anybody have? So constitutional isomers, I think, is the right answer, right? So we'll put that down. We can save some apples for the beginning problems, and then the other ones where you have to draw like resonance structures, we can. You do. That's okay. So let's see. This is constitutional isomers. Did anybody have anything else? Yes, please. So you.
Well, I did. I realized what was going on now is that I wasn't accounting for like the hydrogens.
Oh, I see. So you said they were neither.
Yeah.
You said neither. Okay. Yeah. So be careful, right? That's a very good point you're bringing up here. Because there are the hydrogens here, right? So you draw, if you draw them all in, if you're uncertain on the exam, just draw in all the hydrogens. And then you see that there's the same number of hydrogens actually, right? So that's why they are constitutional isomers. I'll just draw them in quickly. Right? In case of doubt, spend 2 minutes drawing all the hydrogens and count them. Okay? Good. Next one. Any other questions about this one? Is it good? Let's do the next one. Did I skip one or that? This is number 2, right? Yeah. Okay. What do you guys think? Who is for constitutional isomers? Nobody. Okay. Good. Who is for resonance structures? Okay, me too. Okay, so these are resonance structures. I'll just underline it here. These are resonance structures. And again, I want to say again, what's the difference between constitutional isomers and resonance structures? It is that resonance structures in resonance structures, we don't break or change any single bonds. Right? The only thing we are changing in resonance structures is either where the lone pairs are, or where the charges are, or where the double bonds are. Okay? But then for constitutional isomers, we are actually breaking where the single bonds are in the structure. Does that make sense? So if you're ever confused, think about that. Resonance structures, we never break or make new single bonds. Okay? Let's see, next one. Again, are they constitutional isomers? Who is for constitutional isomers? Nobody. Okay, good. Who is for resonance structures? Nobody. Okay, who is for neither? Okay, yeah, good. So you guys are pretty good at this stuff. Huh? So neither is correct. Why is neither correct? Because the charge is not the same. Okay? Are the hydrogens, the number of hydrogens, are those the same? Oh, neither. Okay, so then it's an easy one. But if you look at the practice exam, okay, I think I had something like this. I don't know if some of you might already have looked at the practice exam. I had this one versus, have you guys looked at it? Had this one versus this one. So what are those two? Neither, because the charge is not the same. Okay? But here the number of hydrogens is exactly the same. Right? Because you have one hydrogen attached to each carbon here. So be careful. Okay? If the charge is not the same, then it's also neither. Okay? Good. So it's like a monotone.
Constitutional isomers have to have the same charge.
So yeah, question is, I'll just repeat for the recording.
Okay.
The question is whether constitutional isomers need to have the same charge. The answer is yes.
Okay.
Absolutely. Okay, so we'll go to the next one. Okay, this one. What do you guys think? Constitutional isomers? Yes, good, okay. These are constitutional isomers. So, not resonance structures, because the way they look, right, it's completely different molecule, the way the things are bonded together. And neither is not the case either, because they have the same number of carbons and hydrogens. So as long as the molecular formula and the charge is the same, they are constitutional isomers, unless they are resonance structures. Okay? So I think that's the end of this first problem, right? So then we can move on to this one. This is more interesting now. So, right, this is the allyl cation. So this is the allyl cation. Remember, we had the allyl cation in class. We drew the orbitals. Yeah, we did. I remember. We drew the orbitals and many people were confused. Remember all this orbital diagram and stuff. That was all for the allyl cation. So now we have a couple questions about it. So what's the bond order for each carbon-carbon bond? First of all, what does bond order mean? Bond order means, so if you have a single bond, the bond order is what? 1. If you have a double bond, the bond order is 2. Right? And if you have a triple bond, the bond order is 3, etc. Okay, so if you have a 0.5, like a 1.5 bond order, it means it's between a single bond and a double bond, for instance. So who wants to try this? I'll give out an apple for this one. This is a harder one. Maybe you can do part A and B then, right? Yeah. Try it. Yeah. Try it out. You get an apple regardless.
Awesome. That's what I care about.
That's what matters.
Okay, let's see.
Okay.
So you can talk a little bit into the icon.
Here we go. So first one, it's going to be, so just for, okay. Yeah, so for the first resonance structure, I said that the bond order was 1, and then there was 2. And then for the second resonance structure, that it was 2 and 1.
Okay, so this is right. This is right for
Okay.
the resonance structure.
Okay.
Right?
Okay.
But now remember, so what I actually want for the question, the correct answer I was like looking for
Is that the
1.5.
Okay.
Right? And why?
Oh, because it's...
Because remember, the resonance structures are not switching from one to the other, right? So it's not like switching that sometimes the double bond is on the right and sometimes it's on the left.
Okay.
What it actually is that the structure is really, the double bond is half on the left and half on the right. So in reality, the bond order between those carbons is always 1.5. It's the average of the two, always, right? It's not switching. So that was the answer I was looking for. Exactly, this is the picture I was looking for.
Good.
Perfect. Thank you so much. Mm-hmm. And then I think part B, you pretty much almost answered part B, right?
Oh, sorry.
So let's move on to part B. I have to push this button. Okay? So the question now is how much positive charge, right, is on each carbon atom. You had delta plus, so how big is the delta plus? I guess that's the question. 0.5, right? Does it evenly distribute? I think it's a nice apple.
Oh, thank you.
Okay, thank you. All right, perfect. Any questions? So now let's look at the third part, which I think is more interesting. Okay, so if we have a structure like this, I have an NH3 plus there. It's pretty similar, right, to the other structure we just had, to the allyl cation. But why can't we draw analogous resonance structures? Yes.
Because...
Yeah. We're just talking the iPad. So,
Okay.
maybe you can draw something if you like.
I'll try
Yeah.
to draw.
Exactly. Absolutely right. He breaks the octet rule, right, in this case. Because we have, let me throw you an apple, okay. So this breaks the octet rule where on the nitrogen, right here. Okay? That's the problem. And so I will take it off. Right? So the difference is, let's see, do you think you can catch it? No, I don't. I'm worried I'll throw it. What's that? Here we go. Okay. Yeah. All right. So essentially, bless you. So what you have to see, okay, and I'll generalize this a little bit. What you have to see is that a plus charge is not always a positive charge, a cation next to a double bond is not always sufficient to have resonance structures. It depends on what kind of plus charge you have. Sometimes you can also draw resonance structures where you, as long as you need to have an empty orbital there, right on the carbon next to the double bond, which can accept electrons, which does not. So you need, actually what you need is really something like this, where you have a double bond. I'll say need. Whenever you can draw, you need something like this, where you have an atom which has have an atom there, and then you have a double bond, right? The only way you can draw a resonance structure in this manner is if A does not yet have a full octet, right? Because you're giving it A, if you're doing this kind of arrow pushing here, you're giving A 2 additional electrons. Does that make sense? You see that? And so whenever A does not have a full octet yet, then you can do this kind of arrow pushing. So let me show you a couple examples, right? One example is, I'll just put it up here, where, so A could be, for instance, a carbocation, something like this, right? Sorry, always the circle looks ugly because I'm doing it too fast. But you see a carbocation, right? Because there, the carbon does not yet have an octet. Remember, it doesn't have a hydrogen because it's a positive charge. On the other hand, if you have something, let's say like a carbanion, then you already have a full octet because you have a lone pair on the carbon, so you can't do it, right? So this is bad, so we take that off. Another case where you can have it, for example, is a boron, right? Boron, something like this. There you don't have a full octet yet, because remember the boron is in group, group 1, 2, in group 3, right? In group 3, that means, in this case, it doesn't have a formal charge, and so it doesn't have a full octet yet. You can see that? So if you have a double bond next to a boron, then you can start to draw a resonance structure, like what we had below. I'm trying to think of other examples here. But then again, with nitrogen, if it's like this, because N+, which is in group 5, looks like this, it already has a full octet, so you can't push electrons to it. Does that make sense? So this is the general rule, okay? And it's not just a plus charge, you need to think about whether the atom has a full octet, whether you can give it more electrons. Okay, good. I already gave you an apple, right? Yeah, that's good. Okay, so we move on. That's a very important, questions.
If it was like NH3 and there was a minus instead of a plus, could that work?
So let's see, the question is if it were NH3 and then a minus instead of a plus. Can you draw an example? Let's put an example back up here, maybe in the, in that little corner. If you try, see if we can fit it in there.
So if it was like the one on the bottom, but it was more like.
So first of all, you can't have NH3 minus.
Yeah, but like, if it was like a minus instead of a plus.
Oh, I see what you mean. Okay, let me try to answer. Oops, there we go. Oh. Don't worry, it's pretty stable. It's pretty stable.
Or we like didn't have a charge.
Yeah. Let's see. Yeah, you can do it the other way around. I know what you mean. You're right. So let me see what we could do. For example, with NH3 minus, so you can't have NH3 minus, this will be NH3 plus, right? Mm-hmm. Just based on the formal charge. But what we can do is we'll put, for example, N, you could have NH, and then that would be minus, right? Yeah. So now what you can do is, now you have, this is a different resonance pattern now, right? So what we have here is now a resonance pattern, a lone pair next to a double bond, right? And yes, we can draw resonance structures, but we push the arrows in the opposite direction, right? So what we would do is like this. You see that? Now we are moving around the negative charge, or the lone pair. You see in the other example, with the allyl cations, you see here we have 2 arrows, which is great. It's a bit, but in the other case, we had just 1 arrow and we were pushing in the other direction. You guys see that it's fundamentally different type of resonance pattern, right? We had those 5 resonance patterns. This is a different one. But yes, you could do it in this case. Very good point. Okay, I'll get you an apple for this too. This is a good contribution. Okay, can you catch it? Yeah. Yeah, pretty good. Okay, so any other questions? You guys are good? Let's move on. There's a bunch of questions. Okay, now resonance structures. Lots of resonance structures. Anybody want to draw them? Yes. Okay, so you don't need to redraw the first one. What we're going to do, we'll put a bracket and then do like this, right? And so you can just draw.
How do I change the color to red for the arrows?
You just click on this guy.
Oh, okay.
Yep. And then you will see selection of colors. You need to pick like pink or something. Perfect, that's right. So here's one thing. Hold on. This is good. This is very nice. One general thing, and this is because we just started to draw it on this. So you want to draw it either from the negative charge or from the lone pair. So the very best thing to do is, let me just do this, right? This is a minor thing, but you know that's why it's good to have you guys draw it. So look, so we put in the lone pair. That's what I would recommend. You draw in the lone pair, and then you draw in the arrows, right? But remember, the arrows should always start from the negative charge of the lone pair. Okay? So you might have to switch it back to black.
Mm-hmm.
So it's a minor thing, but it's still something to pay attention to. Perfect. Yes. But it would be okay to just draw it from the negative charge as well. That's fine. You don't have to absolutely draw the lone pair. Perfect. This is awesome. And then you don't have to, if you draw me the arrows in one direction, right, you don't have to draw me the arrows to go back from the product to the, from the right side to the left side. That's fine. Okay? And sometimes I might not even ask for the arrows. Thank you. I might not even ask for the arrows, in which case, it's fine if you don't draw them. But make sure, if I ask for them, that you actually draw them. Okay? Next one. Here we go. Who wants to try this one? I will start. I'll put like this. Okay. But never forget the brackets. That's very important. Put the brackets and don't forget that it's a special kind of arrow, right, for the resonance structures. Yes. Let's see. I'll get an apple already. I'm starting to run low on apples, so you have to do it. Okay, here we go. Yeah. Let's see. Yeah, and let me hold the apple so you can actually draw. Perfect. So, yeah. Make sure you draw the arrow nicely in the middle of the bond, right? When it forms a double bond. Okay. The first one, right? So that's fine. We might want to do it in red too.
Oh.
Do you mind? Let's see. We will just undo it. Give you another shot. Okay. So you click on this guy, the left one. Yeah. This one. Stay on it a little bit. Let me see. Like this. Perfect. Here we go. Okay. So draw it right in the middle of the bond. Perfect. Yes. Because you see, so you want to be very clear where the arrow points to. Okay? If you point it, thank you. Do you want to draw the structure? What you get
sure,
out?
yeah, sorry.
So we'll switch it. Sorry, switch it back to. Yeah. Don't worry. This is great. Sorry, I deleted your arrow. This is really silly. Okay, we'll put it back. So we want to switch to black. Okay. And then let's try to draw the structure. So yeah, be very clear where you point to with the arrow and where you start the arrow. Right? If it makes a double bond, a new double bond, you point right in between the bond. If it makes a lone pair, the electrons make a new lone pair, you point directly onto an atom. Perfect. Okay? Wonderful. Thank you. Super. Okay, so I will add one more resonance structure. Okay? So this is a tricky one where you can have one more. Okay, you see we can now, because you see I say draw as many resonance structures as you can. Okay, so we can draw one other one. You see where we can push it a little bit further, so we can again start it over. Oops. We can do like this. Right? We can just do what we already did. Do it again. You guys see that? And so we'll draw one more here. Oops. Okay, it's still recording. It's great. So I'll draw the other one here. And then again, you put an arrow between, right? So here we go. Okay. So now this looks like this. Good. Any questions? Next one. Do you have a question?
Yeah.
Yeah.
How did, in the very first structure, how did you know that there was lone pairs right there?
How did we know in the first structure, so this one, that there was a lone pair up here? Whenever you have a carbon which has a negative charge, it always has at least one lone pair.
Okay.
So it has something to do with those formal charges. I promise I will upload a video about this. There's like the book talks about this. It's like recognition of these patterns and how many lone pairs it has. The general rule is if you have a carbon with a negative charge and 3 bonds, then you have one lone pair. So if you have, right, or if you have the other way around, if you have a carbon with a lone pair and 3 bonds, then it's a negative charge one. Then if you have a nitrogen with 1 lone pair and 3 bonds, then you have neutral nitrogen. If you have an oxygen with 1 lone pair and 3 bonds, then you have +1 oxygen, right? So it depends on which row or which group the atom is in, and you know how many bonds it has and what charge it has. Does that answer the question a little bit?
Thank you.
So keep practicing that. It's very important that you know. Every time you have a carbon negative charge, you have 1 lone pair. Every time you have a carbon with a positive charge, you have no lone pair but an empty orbital, an empty p orbital. Okay? So we'll go to the next one. Yeah, you want to? Oh, you had a question? Let me try to go back. I just need to get the right, but here we go.
Is there supposed to be an H on that last resonance structure?
The question is there supposed to be an H? Oh, up here?
Yeah.
Yes, you can draw it, or you can also not draw it.
Okay.
That one is fine. So remember, if you're drawing line drawings, you can draw it or you can't. I think both is okay.
Would any of those hydrogens need to be drawn?
The question is, would any of these hydrogens need to be drawn? No.
They're just assumed, right?
Yeah, I just drew them. We drew them, some of them, to help people see what's going on. But you could leave them all out.
All right, cool.
Okay. I agree with you that from an aesthetic point of view, if we drew them in the first 2 resonance structures, it is much better, you know, for anybody to view this with the third one also drawing the same amount of hydrogens.
Yeah.
That I absolutely agree with you. But technically, if you didn't draw that one, it's okay. All right. If it's line drawings, again for Lewis structures, you have to draw them all. So let's go back here to the last one. I think this no, not the last one, is it? Oh my God. Okay, let's move on. Who wants to try this one? I will start. Who wants to try this one? You try it? Okay.
Thank you.
See, the tricky part is the structures all look similar, right? But you. So start by drawing in the lone pairs, because that's where we want to start drawing the arrows. Where do we have lone pairs?
No, oh, my bad.
Exactly. Yeah. And on the other nitrogen too, right? And you see that? Yeah.
Oh, the other nitrogen
Yes,
up here.
very good. So now we have those lone pairs, right? And again, you see there's the NH2 plus that has no lone pair, right? Because the nitrogen has a positive charge. So when you have the lone pairs, then you can get red. So are you getting red? Yeah.
Yep, I got red.
Good. So now we can, exactly, we'll do this. You can take the lone pairs and push them in. You see, if you don't draw the lone pairs, you have a really hard time getting started in the first place, right? And that's kind of mean for me not to draw the lone pairs, but I'll probably do that sometime. It's part of the game, okay? Let's see, yeah. Perfect. So look, it's a symmetrical structure, right? And there's one more resonance structure we can draw. Yes, exactly. So here's one trick. Hold on. Practically to draw. Okay, you can do a different color. That's fine. Yeah. So we'll do that. That will accept. What might be easier in general is you just draw them in a line. And it's also easier to close the brackets, right? And then you don't have to pick two different colors to draw the arrows, because you could just draw the arrows now from the second structure and make a third structure. But this is fine. Perfect.
I did already get an apple.
Oh, you already have an apple.
Yeah.
You have 2 apples. You want another one? Or you're fine? Yeah, it's too many. All right, so any questions about this one? Yes?
When do you know to only start with drawing 1 or 2 arrows versus 1 arrow?
So the question is, let me just repeat it.
Yeah.
So the question is, when do you know whether to draw 1 arrow or 2 arrows?
So like I
Yeah.
started with 1 and then put this positive on the carbon.
I see.
And it's
Okay.
still the same overall charge.
Yes. So let me put what you put down. There might be lots of.
So I got 4 instead of.
Yeah. So you have 4 resonance structures. Again, I will start to do that now from what you did basically is this, right?
Yeah.
And you got another resonance structure, which is a perfectly correct resonance structure, which then looks like this: NH2, lone pair, NH2, lone pair, NH2, lone pair, and a plus in the middle,
Yes.
right? So basically move the positive charge onto the carbon. It's perfectly fine to do, okay? You would say that this is what we drew, however, here is more of a minor resonance structure.
Right.
Why is that? Because we don't fulfill, this carbon does not have an octet, right? Mm-hmm. So no octet here, and so we will say it's a minor resonance structure, but it's still a good one. So how to say this? If you draw me, as long as you draw me these 3 ones on an exam, you are golden, okay? You're fine. If you draw me the minor one as well, like you draw all 4 of them, you are also perfectly fine. Okay? You see what I mean? So I will not penalize you if you draw minor resonance structures. What I might take some points off, if let's say if you only draw these 2, if you only draw these 3, for instance, right? So I want to see all the major resonance structures. But if you draw a couple extra ones, that's fine with me, okay? What is helpful for us to grade is if you maybe highlight the major ones in the end, right? Maybe circle the major ones, say those are the major ones, the other ones are minor. That just really helps us grade, because remember, we grade 150 exams, and it's just going to be, okay? So what I might do instead, sometimes I will just give you, let's say, I will give you a structure and be like, draw the 3 major resonance structures of the following structure, right? So that you know there is 3 I'm looking for, and just give me the major ones. That makes the grading easier, and for you guys, it makes it easier to see what's happening. Okay, I will get you an apple for this one. It's a good question. Okay, thank you. So let's move on, right? Any other questions? Okay, let's go to the next one. Okay, we're getting there. This is a shorter one. Who wants to try this one? You want to get it a try? Not always the same people though, right? You guys always do it. I mean, that's fine. Does anybody else want to try? No? Okay. Oh, you want to try?
Yeah, he can try.
Okay, we'll get you a chance. Because you already did one, right?
No, but it's
Oh, you didn't? Okay, you do another
on the
one.
next one. It's good.
You do this one, and then you can do the next one. Does that sound okay? Yeah.
Sorry.
Sorry, I can't remember who already did.
I'm getting the hang of
Still have
it.
3 apples. Fine, I need to increase the apple share portion.
You can just.
Okay, let's see. Perfect. You put in the lone pairs, yes. So this is again our resonance pattern where we have a lone pair next to a carbocation. Right? Before we had a lone pair next to a double bond, and then we had a positive charge next to a double bond. Right? Those are these common patterns we've seen. Perfect. This is great. Thank you so much. Okay, let's see. We go. Any questions about this one? You guys are good? Okay, let's do the next one. One more. So, you want to try this one?
I can try.
This is a harder one. Sorry, Egg. Try it. It's fine.
So, on the
Yes.
question, like, how many examples you want us to do with the arrows in it?
So the question is whether on an exam, whether I want you to draw the arrows. That's a very good question. I will specify what I want. I don't know. I think it is helpful to draw in the arrows. I believe it is helpful for you guys. What I might be looking for in the end is just the correct resonance structure. So what I've done last time, I remember, if I remember correctly, on the last exam, I split the question up into two questions. One of the questions was I give you all the resonance structures, or I give you two resonance structures, and I ask you to draw the arrows to go from one to the other. Okay? And then at the same, and that was like question 5 or something, I don't remember which one. And then there was another question where I gave you like 3 boxes, I think, and was like draw the major resonance structures of the following compound, right? And why do I split it up into 2 separate problems? So that you have a chance to get, if you get part of the problem not right, then you can't do the second part of the problem, you know what I mean? Which to me is always a problem. You know what I mean? You get problem A wrong, that means you get problem B and C wrong, and so that's not the nicest. So I try to do it separate problems, and it's also easier to grade that way. Because we see where you draw, I give you a framework to draw in the arrows. Okay? So just for the exam, I recommend whenever you draw resonance structures, draw in the arrows. Because it helps you figure out what's going on. But on the exam, you really have to just answer what I'm asking for. Okay? Sometimes I might ask you to circle something, and if you don't forget to circle, bad. Like it's not the same, it's just I make the exam with grading in mind as well, so it's easier for me to grade. So really pay attention to what I'm asking. Just read very carefully. I'll put stuff in capital letters and try to be very clear. If there's any questions about what you have to do on the exam, like whether you have to do that or that, feel free to ask me a question. I'll try to be there, or the TAs at least, and they can text me. Okay? All right, so let me see what you wrote. This is great, okay? Let me see. So the arrow pushing is great. I'll just make it red, okay? Because I just love the red colors. Okay, here we go. And this is a great structure. I think there is one more resonance structure, right? We can draw. Do you want to try?
Oh, sure, yeah.
Let's see. I will take the arrow out on the end, and so maybe you can see if you can do this directly. I'll shrink it a bit. Let's see, so we get some space. Sorry, I didn't notice that it's actually because the one is fixed, right? Can't shrink it. Okay, so let's see. We take this out again, and we're gonna do like this. And so see if you can draw the arrows. And maybe, let's see, here we go. Okay. Thank you. 2 more apples, those are one for you, one. You're welcome. Let's see. Thanks.
Thank you.
Perfect. Exactly, you can put
I don't know how to change the color.
that's fine, don't worry about it. So this is great, okay? So you can put the double bond, the positive charge in the middle. So, let's see. So basically the general rule, right, is if you have a double bond, one double bond next to a positive charge, you can draw 2 resonance structures, right, where the positive charge is either on the left or on the right. Then if you have an additional double bond conjugated right next door, you can draw 1 more resonance structure. If you put in 1 more double bond, you can draw another resonance structure. And another one, another resonance structure. Does it make sense? So that tells you how many, depends on how many double bonds there are. Then there is if there's 2 double bonds, there's 3 resonance structures. If there's 3 double bonds, there's 4 resonance structures, etc. Does that make sense? If they're all in a line. Okay? Good. I will just close the brackets and we move on, okay? So I think we're done with this problem now. Yes. So this is now the type of exam question I mentioned. I would give you something like this, where, I give you two resonance structures, ask you to draw in the arrows. So who wants to draw in the arrows? Yeah. Thank you. The other thing is we might want to draw in here the brackets. Okay, so you can, thank you.
Is this red? Did you want it red?
I made it red already.
Okay.
I prepared everything. So all you guys have to do. Yes, exactly. So perfect. This is great. Thank you very much. I don't have any apples anymore. All right. Any questions about this one? In general, okay, I had a couple people at my office hours, and sometimes I notice you have to be very careful the direction in which you draw the arrows, right? If you draw, for example, in this situation, if you draw the arrows the other way around, from the oxygen downward, then it's all wrong, completely wrong. Okay, so be very careful when you grade yourself, when you do problems, that you draw the arrows in the correct direction. Okay, so let's go to the next one. This one. Now this is related to, remember we talked about this for a little bit back in lecture, where it depends on whether the lone pairs, whether they are localized or delocalized, and they can be complicated. So in this case, what do you guys think? Is it, so for, let's see, we have two options. Lone pair on nitrogen, right? So this lone pair, is it localized or delocalized? What do you guys think? Localized? So you guys are all for localized. No, some people are for delocalized. So I am for localized. Okay? So that's the correct answer, I think. Unless I'm wrong, which should not happen. Sorry. So let's discuss. Why is it localized? Why is it not delocalized? Can anybody explain it? Yeah. You want to explain? Yeah.
Because if you try to move the lone pair anywhere, you violate the octet rule of all the other atoms. Do you want me to write it?
No, that's not necessarily true, but try to write it. No. Let's see. Can you draw a structure? Draw a structure.
Oh, you want me to
So I don't think it's because you're violating the octet rule. It's because of this weird thing we discussed in lecture where the lone pair is not aligned with the pi system.
Oh, yeah.
So it's not, because let me show you. I will draw a structure where we can theoretically move the lone pair, which looks like a reasonable resonance structure. Okay, I'll do that for you guys. Let me show you. So if you do this, so this is a really more complex kind of problem, right? So we could do this. We could take the lone pair and be like, okay, look, we have a lone pair next to a double bond, right? So why not do this? Right? You're not violating, You see, then you're not really violating the octet rule. See that? It just looks like a weird structure, but let me show you. So 5, here we go. So then you would get a negative charge on this carbon, right? Because you only have one hydrogen here. So actually the octet rule is not violated, and you get a positive charge here. Okay? You see that? So the answer is not that simple. Why is it localized? Yes? Yeah.
Oh, me?
Either, yeah. Well, you might get different answers too. There's different reasons you can answer this.
Is it because then when you have the two, do you draw or?
Yeah. You can try to draw it, or I'm just holding it near so that people can hear, the recording.
When you have two double bonds, then it will make it an sp2 hybridized, and then it would become a linear
structure, and it would be super strange because you're trying to bend the linear structure here on the nitrogen into a 5-membered ring.
Yeah.
Right? So that's a perfectly good answer, right? Yeah. I think that's the one I had on the board in lecture. So did you have a different answer? Same answer?
Wasn't it like you do this one structure one time where like it had the two on top of each other?
So yes, exactly. So the other way, so one way you can answer this, right, is that you don't want to have a nitrogen which is linear, like sp hybridized, right, which is kind of linear, and then try to bend it into a ring. Okay, because that's super strained, so it's not a good resonance structure. It's a really bad resonance structure. But then the other way you can explain it, which is really the best way, frankly speaking, is, you know, in the ring, so I'll try to draw this kind of sideways, but if you look at the ring sideways, so the oxygen would be back here, nitrogen is kind of, this is coming forward, now this is in the front, so I'll make it a little thicker, okay, and then we'll have, here would be, so it's kind of, this is almost like a Haworth projection, right, from the side, and now we will have a hydrogen here, hydrogen coming forward, the lone pair in the plane, right, and another hydrogen over here, you guys see that? And then a lone pair on the oxygen, and another lone pair pointing back. So now, you see there's all these double bonds. The double bond here has orbitals like this. The other, so it's a pi system where all these orbitals are aligned, and actually they, in this case they overlap with the orbital on the oxygen too, one of them, one of the lone pairs, and then these p orbitals have, you know, bottom parts. You guys see that? And now you see that the lone pair here is orthogonal to these other orbitals, so it can't overlap, so it can't make a resonance. Does that make sense? That's the other explanation. Okay? Any questions about this problem? So the answer is it's localized, but you should be able to explain it. I think the easiest explanation on an exam for you guys, rather than trying to draw a picture like this, is probably to just say it's too straight. Am I right? So that's what I would recommend, at least for an exam. Okay? Okay, good. Yeah, one question?
Can this only happen on nitrogen, or could it happen anywhere else too?
The question is, could it only happen on nitrogen, or could it happen on other systems too? It can happen on other systems too. And we have it in this molecule, actually. So the other one, you see, the oxygen, right, is actually also sp2 hybridized. Okay? So the oxygen back here is sp2. That means we have a p orbital which overlaps with the pi system. That's the one I highlighted in red and blue. But the other orbital, which is pointing back here, it's now orthogonal. So that also cannot overlap. So one of the lone pairs in oxygen is localized and one is delocalized. Does that make sense? So yes, it can happen with other atoms too. It can happen with nitrogen, it can happen with oxygen, it can happen with phosphorus. You know, any system which has lone pairs, basically. Could even happen with some carbon-based systems. Okay? Good question. Any other questions? So practice that. I think the book has some practice problems on it. Let's see. Next one. I think we have 2 more problems. Or 3 more? 3 more? Okay. 2 more? Okay. So we're getting there. 3 more? Okay. Let's move on. Based on what we know about the strength of acids, is the amine base 1, so this thing, strong enough to remove a proton from ester 2? So this you will have to look at pKa tables. Does anybody have the pKa table in the book? And I don't remember the pKa. I mean, I remember roughly, okay? I think the pKa of this amide base is somewhere around, let's see, somewhere in the 20s, okay? Around 25, I think. But roughly, okay? Now, it's, or maybe even 29, something like that. Now that the pKa of an ester is fairly, it's a little bit more acidic. So that's around, it's around 20, I think. And so now, of course, if I'm saying the pKa of this, I don't actually mean the pKa of this thing. I mean the pKa of the conjugate acid, right? So what I mean is the pKa of NH3, right? the pKa of NH2 minus, of course you could remove another proton, you get NH2 minus, is enormously, that never happens, okay? So that's probably like 50 or even higher, okay? But for NH3 going to NH2 minus, the pKa is around 25. So now, that means, that means that the reaction will happen, right? It's strong enough. So now the first question is, can you draw the products of the reaction? Where does it take away the proton? And I kind of already drew it there. It takes it away from this position. Why? So let me show you. Let me take off some of these. Let me take some of this stuff away, okay? So we get some space. And we'll say yes for answer A, for part A. Now, for part B, you basically have to do this. You have to draw in the protons, or the H's, the hydrogens, right, which would get removed in the acid-base reaction, because this NH2 minus is the base. Okay? So you have to draw in the hydrogens, and now you have to think which one of these hydrogens, based on the Oreo principle, is the one which is most likely to be removed. Okay? What do you guys think? First of all, what does Oreo stand for? The A is for the type of atom. Okay? Is there any difference in the type of atom where you would form the negative charge after deprotonation here? No, because they're all carbon atoms. Right? If you take the hydrogen away from here, you make the negative charge on this carbon, so it's going to be on a carbon. Right? If you take away... Sorry, this looks like H2 down here, so I'm going to take the 2 away, okay? Otherwise, that's going to be really confusing. Okay, so we'll take this away. So this is just compound 2, okay? So if you take away the proton from here, if you deprotonate over here, you get the negative charge on the carbon as well, right? Now, if you take away a proton from here, again on the carbon, no difference. And from here, again on the carbon, no difference. So the A, there is no difference on the A level of Oreo. Make sense? Now, what's the next thing we look at? What does the R stand for? Resonance. So now we have to think about, okay, we take away a proton from all of these positions. Which position can you take a proton away? Then you get a lone pair there, and then you get resonance structures. Right? So to figure that out, you have to be already pretty good with resonance structures. You see what I mean? Because you kind of have to, in the head, draw resonance structures or figure out which ones have resonance structures for all of these possible products. See what I mean? That's why you have to be really good at resonance structures. So what do you guys think? There's only one position where you really can draw resonance structures. Which one is it? Yes?
Is it not those bottom two, the one next to the double bond?
Right above the 2.
Yeah.
Yes, exactly. These 2 protons, they're the same, right? Doesn't matter which one we take off. So, so these 2 are the ones. So we will, right? So let's draw the product, okay? And then the reason for those products is because of the resonance structures, right? That's why. Then we ask which is the more stable resonance structure. So I will draw it. Is that okay? Or does anybody really want to draw it? I'll do it, okay? So we get 2 resonance structures. First of all, I'll draw it as a line drawing, right? So this part of the molecule stays the same. Now what do we get if we take away the proton? We just get a lone pair and the negative charge on the carbon, right? So here we would have the lone pair and the negative charge. Okay? Now that's great. Now we draw the other resonance structure. So we do like this. That's the same as what we did before, right? So same, it's like again this resonance pattern, lone pair next to a double bond, and so we can draw the other resonance structure. Sorry, this is bad. I need to draw the other one. Okay, here we go. Here is the other resonance structure. Ta-da. Right? So far you're good? Now which one is the more important one? Left or right? That's the other part of the question.
Right.
The right one. Yes. Why?
Because oxygen is more.
Yes, because oxygen is more electronegative. So this is the major, we call it major resonance form, right? And we'll say because oxygen is more electronegative than carbon. Okay, good. Yes, question.
How did you get the lone pair on that first resonance structure?
How did we get the lone pair on the first resonance structure? I will draw you a reaction. Okay, so you can draw arrow pushing for this stuff. Let me show you. So that would be another question I love to ask on an exam. So something, this is, I would give you something like this, right? And be like, so these are the products. Okay, so this is the starting material. Now we are doing an acid-base reaction. And you need to be able to now draw these arrows, okay? So we'll draw in those hydrogens. And what do we do generally? Do you want to try drawing? Are you willing to give it a try?
I'll try it.
Give it a try, okay? This is a hard thing, okay? I'm putting you on the spot here.
Yeah.
So this is essentially an acid-base reaction,
Okay.
right?
Yep.
So remember, don't worry about it. It's pretty stable. Zoom the recording, so that's fine. It just opens Siri, but that's fine. So remember, when we draw an acid-base reaction, where do we start the arrow? Always on the base, okay, on the lone pair of the base. Like when we did resonance structures, you started on the lone pair.
Okay.
So you started on this lone pair.
Yeah.
Yes. It doesn't matter which lone pair. Sorry, it's like just trying to paste something. That's, yeah. Let's see. So you try again. Yeah.
Okay. So.
You started here. Yeah.
Yeah. And
then you go to the hydrogen, which you're going to remove.
To this hydrogen? This hydrogen?
Yes, you go to the hydrogen.
Okay.
Exactly. And now you see, what are we doing? We are starting to break the octet rule on the hydrogen here, right? Because it's making too many bonds.
Yeah.
So you have to now break the bond between the carbon and the hydrogen, between the acid and the H.
Okay.
So this bond here.
Right
Yes.
here.
Yes.
So.
But so the reason it's trying to paste is just
You can
because.
take this one, right?
Yeah, you try.
Pull it over.
Try it. Yeah.
Right, don't you take this?
Yes, and you pull it to the carbon. Not like this.
Oh, not like this.
Let me show you. Okay, let me show you. That's why I want you guys to try it. You do like this, you see? You push it to the carbon. And this bond here becomes the lone pair. That's why you after get the lone pair on the carbon.
Yes, yes, yes. Okay.
Does that make sense?
It does make sense.
So, but this thing you guys have to practice, okay? This is fairly new because we just talked about it recently in lecture.
Yeah.
But it will be on the exam, this kind of arrow pushing, okay? If you look at last year's exam, I think this was the last question on the exam. And it's a hard one. It's a hard one, okay? This stuff you have to practice, this arrow pushing. It's very similar to the resonance structures, but here we are now breaking single bonds, you see? And the arrow pushing shows you that this becomes, so this bond now here becomes the lone pair. That's why and then it becomes the negative charge, right? Because you lose H+.
It's more of like with the bond line drawing, it's harder to visualize. Like,
Absolutely. With the bond line drawings, it's harder to visualize.
yeah.
Everything is coming together now.
Yeah.
And I'm not saying this is easy, okay? I put you on the spot. Thank you so much. This is good. But if you draw it, it's like you will never forget it.
Yeah.
And other people will also feel like the thrill of,
Yeah.
you drawing.
Absolutely.
If I just draw it, you just watch me draw it, it seems like easy, okay? But it's not. All right, let's move on. Any questions about this? There's one more question down here. What would happen if water were present? Generally, you have to do this reaction without water. Now, if water is present, what's the pKa of water? 15.7, right? Or something like that. We said in lecture, 15.75. Now water, that means water is more acidic. Remember, the lower the pKa, the more acidic. So then, in this case, the water would just be deprotonated. You would form hydroxide, like OH-, and you would not deprotonate, because this has a higher pKa, right? These protons. You would never get the reaction to happen. You would just deprotonate water. So that means when you do these reactions, or this reaction, you have to make sure there's no water present. Okay? Sounds good? So in lecture, we'll talk about this briefly on Friday again. It's called the solvent leveling effect. But it's just a fancy word for saying that if water is present, you would just deprotonate the water because it's more acidic than the stuff you have. Okay? Let's do the next one. Okay. This is a little bit easier. It has something to do with resonance structures, right? So basically, again, when we protonate with H2SO4, and I will draw you quickly the arrow pushing for how this works, okay? Like before. So we can do a protonation reaction, acid-base reaction. So you need to be able to draw H2SO4, right? Which has, you've done this in Gen Chem, right? H2SO4 looks like this, okay? Sulfuric acid. And now, does anybody want to try, draw the arrow pushing to go from here to here? Like what we just did before. Anybody want to give it a shot? On the spot, you want to try? No worries if you get it wrong, okay? So the first thing you want to do, remember we always start at the base, okay? We start on a lone pair, we start the arrow at the lone pair of a base, of the base. So which one is the base?
It's the acetic acid.
The acidic acid, okay? So that's confusing, right? Because it says it's the acid in the name, but actually it's the base here because we're using a much stronger acid, like sulfuric acid, to put the proton on to this, or what's already an acid. So that means you have to now, because acidic acid is the base, you have to draw in the lone pairs on the oxygens, right? Perfect. And maybe one more lone pair on the second oxygen. Yeah, perfect. And now let's switch to red. So just stay on this one. Yes, and now pick a red. Perfect. So now see if you can draw, just click back. Yeah. So see if you can pick any of those lone pairs. Maybe to get to the first structure, you pick this lone pair, right? And then you attack, with that arrow, you attack the H, yes. And now you need to, again, you see you're making too many bonds to the H, so you need to break that bond. Yes, perfect, right? Very good, okay? So this is the arrow pushing. You start to get the hang of the general pattern now, right? Always the base, the lone pair attacks the H of the acid, and then you push the AH bond to A, okay? So now, so this leads to this resonance structure, right? But then, of course, we can draw resonance arrows. To do this, we can be like, okay, here. No, that's not right, actually. So these are not resonance structures, okay? Why are they not resonance structures? Because they have the more single bonds, right? So they are actually constitutional isomers. You see that? These are not resonance structures, they're constitutional isomers. So which one is preferred? What do you guys think? The one with more resonance structures. So which one can you draw resonance structures for? The left one, exactly, but not for the right. For the right one you can also draw, but they're all crappy resonance structures. For the, I mean, or not crappy, I mean just not very important ones. But you see for the left one, this is our standard situation, lone pair next to double bond. And so here you can draw a resonance structure like this, right? And I'll just draw it like upside down here. So this other resonance structure looks like this. OH, lone pair, double bond, H, and the plus over here, okay? Good? That's what's going on. So that's why protonation on the oxygen which has the double bond is preferred over protonation on the other oxygen. Okay, because you can draw more resonance structures in the product, and resonance structures stabilize the structure. Okay? Good. I think we can move on to the last question. You guys good? Yeah, one question.
Does it matter which hydrogen you use? Single bond on?
The question is, does it matter which hydrogen you use to put, you mean in the sulfuric acid?
Yeah.
Like whether we use this one or this one?
Yeah.
It does not matter. They're exactly equivalent. So you can use either one of them. Okay, good question.
But if one of them was, like one of those oxygens were a carbon, then it would matter?
Yes, if one of those oxygens were a carbon, then it would absolutely matter. Then you would want to use the one which is on the hydrogen attached to the oxygen, right? Because of the REO principle. Okay, because the oxygen is more electronegative. Yes. But in this case, they're both oxygens. They're symmetrically equivalent. They're the same. So it doesn't matter which one you take. Okay, good question. All right, let's go on to the last question. You guys are good? This one. Okay, phenol, that's phenol. Really toxic. And this methanol is also really toxic. Methanol makes you blind. Phenol causes like cancer. So neither of those things is good. But they're both, and then ethanol, is also really toxic, but less than methanol. So if you have methanol poisoning, they will give you like ethanol. You know that, right? Yeah. Okay, but you see the pKa values are very different. 15 versus 9, around 9. Okay, why? You can give it a try. Let me see. You want to draw? You probably need to draw something. Try to draw something, or just write like a sentence. I've written it down. Yes, exactly. So because phenol has resonance structures. Okay. So that's partially correct. Okay. So this is partially correct. I think I would give you most credits. Okay, on an exam. Okay. So but why is it not 100% correct? Yeah, it's different. Okay, it has different hybridization. That's right, actually. So you could explain that way. No. It has something. This all has something to do with resonance structures. Absolutely. But the resonance structures we want to look at are the resonance structures of the conjugate base, right? Remember what we want to do. What we are looking at with the Areo principle, is you take AH, right? In this case, phenol, right? And you take H plus away to make the conjugate base. So the conjugate base looks like this, O minus. Okay? So that's the conjugate base. So what you want to say is that the conjugate base of phenol has many resonance structures, and so that the conjugate base is very stable. So the acid likes to give away the proton to make the stable base. Right? If you say that phenol itself has many resonance structures, you actually say that you stabilize the acid, and then it would be a very stable acid. It wouldn't want to really give away the proton. Does it make sense? So the reason actually, you see both the phenol and the conjugate base, the phenoxide, both are stabilized by resonance structures, but the phenoxide, because it has a negative charge, the resonance structures are more important. The resonance actually becomes more important when you have the O minus there, and this is why it stabilizes the product more after you take away the proton. Does that make sense? Because if you would stabilize both the acid and the product equally, then you would not get any benefit of the resonance. You wouldn't become more acidic. Does that make some sense? You guys all look very confused. So basically, the way I'm thinking about it, okay. So I will say the absolutely correct answer would be because the conjugate base, right, of phenol has many resonance structures, or just has resonance structures. So that would be the correct answer. And the way to think about it, I'll take this beautiful picture away, is like this, right? So if you think about an energy diagram, where we have AH, right? And then going to something like A minus plus H plus, right? If that the reaction is somewhat downhill, okay? And so if you stabilize, if you take this thing, the product, and move it lower in energy, then there's a larger driving force to lose the proton, okay? So it becomes more acidic. But generally what we'll talk about this more in chapter 6. But if you have a reaction and the energy barrier is small, or like the energy difference is small, the reaction energy is small, then the reaction has no strong driving force to go to completion. But now if you move the product down in energy, then the equilibrium will favor the right side. Okay? Now if you move both the starting material and the product down equally, for example with resonance stabilization, then there's no stronger driving force for the reaction. If you just lower the energy of the starting material but leave the product alone, then actually the reaction becomes less favorable. Does that make sense? That's why it's kind of a minor point at this point, but in the future it will become important. So always when you talk about this Areo principle on an exam, make sure you tell me that it all has something to do with the conjugate base. Okay? That's really what the Areo principle applies to. Just tell me the conjugate base of this molecule has these resonance structures and drawings. Okay? Thank you guys. And one more question. or we'll talk about it offline. So I will turn off the video here.